for a very beautiful talk.
Okay, thanks so much. Yeah.
So our next speaker is Professor Nathan Seiberg from the Institute of Advanced Study. So can you please?
Yeah, I'm trying to unshare.
Yeah, sure. Yeah, Professor Seiberg, can you please share?
Can you hear me and see me and see the slides?
Yeah, so he's going to tell us about exotic theories and UV-IR mixing. So please.
Thank you. I hope you can see me, hear me, and see the slides correctly. Can you? Is everything okay?
Yes.
Yes, it's all okay.
So thank you for inviting me. It's a great pleasure. Unfortunately, I cannot be there in person. I wish I could, but at least I succeed to see on the side some familiar faces of good friends for a long time. I really enjoyed the previous talk, which gives a nice segue to what I'm going to talk about here. And because I'll mention a little bit fractons, is I was really fascinated by these developments in condensed matter physics. And I felt that they have to fit into the language of high energy physics, which is appropriate, say, for this audience here. And there was a very long pandemic. There still is a very long pandemic. And with a group of fantastic collaborators, Pranay Gorantla is Indian, actually. He was in TIFR. And Odalam and Shuheng Shao, we have been working for the last 2 years or so on these exotic models, trying to understand them in the language of quantum field theory in high energy physics, which is really distinct from the language of condensed matter people. And I found that really an eye-opener and extremely exciting. So as a way of introduction, it will have a little bit of overlap with the previous talk, but my perspective is a little bit different. So there is a law that I've learned when I was at the beginning of graduate school, and long before most of you were born, that whatever you do at short distances doesn't matter very much for the long distance physics. Most of the information about the short distance theory is washed out by the time you are at long distances. This is the reason it's convenient to organize the classification of phases and phase transitions between them in terms of the low energy effective field theory. So the law is that low energy, and I try to be consistent with the colors. This is my infrared or low energy, and this color is the UV or short distances. So the law is that the behavior of every lattice with short range interactions is captured at long distances by standard quantum field theory. So that is very, very useful because the quantum field theories are characterized by a small finite number of parameters, whereas the short distance Lagrangian or short distance Hamiltonian can depend on a very, very large number of parameters. And that's why this description is effective. And indeed, the technical term for it is effective field theory. So for decades, I was convinced this is right, this is always right, until several years ago, some exotic lattice models came out. I first heard about it, about the work of Ha. Can you see my pointer? Can you see my pointer?
No, actually.
No.
Can you see the pointer
slide,
now?
But not the, yeah, now we do, yes.
Yeah.
Okay, it started with the work of Ha. And honestly, when I first heard about it, I thought, within a year or two, somebody will debug it. This will end up being wrong, and I don't have to bother with it. Well, this didn't happen. In fact, this model of fractons became more and more popular. There are more and more models. This is not going to go away. And there's actually an older paper by condensed matter people, by Paramakanti, Balance, and Fisher. I'll talk more about that one. A model that does not have fractals, but in many ways, it has some of the peculiarities of models of fractals, and it's a lot easier to work with. So throughout this talk, I will focus on this model, the 𝗦𝗀𝗀𝗀𝗀 model, which actually does not have fractals, but it has some of the features that the previous speaker talked about. And as you will see, it's very close to various models that high energy physicists, especially string theorists, like to study. And in that sense, we can borrow a lot of techniques. and yet it poses some of the challenges that models of fractals do. So to summarize this slide, there is this law that has been dominating physics for nearly a century. It's been very effective. And there are some counterexamples that don't fit the law. And we would like to understand what's going on here. So during the pandemic, we have been studying many examples, including known models of fractals. There are many examples in the literature. And we reproduced using our language some of the results in the condensed matter literature, but we also found new results about the same models. And we also found new models. But it would be more effective to start with one particular example. And this is this 2+1 dimensional models, my terminology about dimensions, so that I can talk both to condensed matter physicists and high energy physicists. 2+1 dimensions mean 2 space and 1 dimensions. And since 2+1 is 3, this is what in high energy physics called 3 dimensions. So what did Paramakanti, Balance, and Fisher do? They considered the 2-dimensional lattice and wrote a Hamiltonian model. I'll do it in Euclidean space. So in Euclidean space with the Lagrangian, I have also a lattice in the time direction, and we have an action. We have a phase at each side of the lattice. And in the time direction, we have cosine of delta tau phi. So this is kind of the standard interaction as in the standard XY model. In the standard XY model, in the spatial directions, we look at cosine of the difference of phi between 2 neighboring sides, whereas here we go around the plaquette and we take linear combinations of the phi's around plaquettes and we write the cosine. So this model is well defined. We can put it on the computer. If we have a finite lattice, we have a finite number of integrals to perform. The action is bounded from below. Everything is convergent. There is no reason not to analyze it. And this model is interesting for many reasons. One of them is that it has a subsystem symmetry, which I'll refer to as momentum. In the condensed matter literature, this is called charge. In the string terminology, this is called momentum, because you can shift phi, which a priori depends on x, y, and tau. You can shift it by an arbitrary function of x and plus an arbitrary function of y. So you take all the spins, say, in this row, and you can rotate them by a phase, and you can check that this is a symmetry of the action. And we have a separate group element for each horizontal line and a separate group element for each vertical line in the lattice. So that's why it's called a subsystem symmetry. It's not like a global symmetry that rotates all the spins, but we rotate only the spins along one line. And then we follow the law, and the law tells us, that I mentioned in the previous slide, that at low energies, at long distances, the number of lattice sites is large, and we kind of scale and we look from afar. There is a continuum description. And we just follow our nose, and let's assume that phi is smooth. If phi is smooth, we can expand these 2 cosines, and we find this 2+1 dimensional field theory. Unlike the lattice model, this 2-dimensional field theory is free in the sense that it's quadratic in phi. The only subtlety here is that phi is a periodic variable. So phi is identified with phi plus 2 pi. So this is very similar to actions that field theories like to study, and it's good to keep in mind the corresponding 1+1 dimensional version of it, where instead of dx dy, we have here only dx squared. This is the compact boson, and there's huge literature about that. So this model seems free. It is free, and it seems straightforward to analyze, but it turns out to be extremely subtle. And I'll point out some of the subtleties in this model. So for the rest of the talk, I'll concern myself with 2 questions. One, what is the relation between this lattice model and this continuum model? This looks like a straightforward question. The answer turns out that it's not. And the second question, how should we think about such continuum field theories, which have this structure of derivatives and have that such a subsystem symmetry? And again, this looks misleadingly simple. In fact, this is quite complicated and so on. So these are the 2 questions which look really easy. The goal of the talk, usually in the talk, you look at a complicated question and you answer it. The goal of this talk is to present simple questions and show you that the answer is actually complicated. So this is the model we should study. And it has a subsystem symmetry. And we can ask, what does it look like in this continuum notation? In the continuum notation, since we have a continuous symmetry, there should be a net current. And the method procedure tells us how to find the current. So the current satisfies a very interesting conservation equation. D tau J tau is not dx Jx plus dy Jy, but it's dx dy Jxy. So we have double derivative here. As a result, the conserved charges are normally obtained by integrating the temporal component of the current. But here we can integrate either along y or along x. So along x at fixed y or along y at fixed x. And because of this conservation equation, these charges are separately conserved. So this is what the subsystem symmetries look like if we wanted a local characterization of them using local conservation equation. And this action has two such conserved charges. One of them is the one I'll call momentum. This is the current, this is the time component, this is the space component. And the equation of motion of phi shows that it is conserved. If we try to perform this transformation on the action, it shifts phi by a function of x and a function of y. And notice that these functions can be discontinuous. We can shift only at one value of x and not touch what happens at the other value of x. So we already see that this is going to be a little bit subtle, because in this quantum field theory, we should also analyze what happens when the field configurations are discontinuous. This model also has another conserved charge, which is not present on the lattice. So this symmetry started on the lattice, and I presented it on the previous slide. But there's also another conserved charge with another conserved current, this one. And if you just hit this one by d tau and this one by dx dy, you see that the two this current is also conserved. And if this thing reminds you of the 1 + 1 dimensional compact boson, which has a momentum and winding symmetry, it's not a coincidence. This looks a lot like the momentum symmetry, and this looks a lot like the winding symmetry, and hence the name. In the condensed matter terminology, this is called vorticity. And if we know our 1 + 1 dimensional compact boson, and it has momentum symmetry, and we know it has winding symmetry, it begs the question of, is there a self-duality? And in fact, there is. We can perform a duality transformation here and exchange mu and mu0. It exchanges the momentum and the winding symmetries. Again, this is very much as the standard XY model in 1 + 1 dimensions. And this self-duality exists in the continuum, but does not exist on the lattice. So this is a peculiarity of the momentum of the continuum theory, which is not present on the lattice, very much as in the compact boson in 1 + 1 dimensions. So what do we do when we have a field theory? First thing to ask is, what is the spectrum? So we place it on a lattice, so that to make things very concrete and very easy. And then we take the continuum limit. And the continuum limit is taking the lattice spacing to 0. And that's kind of this purple violet color, because it's the UV limit, number of sides to infinity with fixed space, size of space. And we find various states. First, they're plane waves. And so we just substitute the plane wave, and we find the energy of the plane wave. And it scales like 1 over the length square. The reason is that the energy is proportional to the momentum in the x direction times the momentum in the y direction. This is because of the structure of the derivatives. So the energy scales like 1 over L square. And comparing with the 1 + 1 dimensional compact boson, the energy there is 1 over L. So we see the energies here are parametrically smaller than for a compact boson. They are of order 1 over the length square rather than 1 over L. There is more density of states at low energies than in the compact boson. The surprise is really with the charged states, the states that are charged under the momentum and winding symmetry. The analysis is completely straightforward. And the surprise is that the energy of the charged states is infinite. The scale is 1 over L as opposed to 1 over L square, but there's a factor of the lattice spacing in the denominator. So as we take the continuum limit, all of them go to infinity. This is to be contrasted with the situation of the compact boson that we are all familiar with, where the energy of the charged states also scales like 1 over L. So in the 1 + 1 dimensional compact boson, both the plane waves and the charge wave and the charged states have energy of order 1 over the length. Both of them are finite, and both of them participate in the low energy conformal field theory. That's not the case here, where the plane waves have finite energy. It scales like 1 over L square, and the charged states have energy of order 1 over L, but another lattice spacing A here. So they are actually infinite in the continuum limit. This is shocking. It's shocking because it means that we have states, all the charged states. So we have some huge symmetry, the subsystem symmetry, and we have some charged states, and all the charged states have finite energy on the lattice, but it becomes infinite in the continuum limit. So the charged states are present in the Hilbert space of the lattice theory, but not in the Hilbert space of the continuum theory. What this thing means is that operators that violate the subsystem symmetry, like the exponential, this is very similar to what we have in the 1 + 1 dimensional compact boson. Such operators are infinitely irrelevant in the continuum theory. So such operators exist on the lattice, but they are infinitely irrelevant in the continuum limit. In the language of the renormalization group, such operators are known as redundant operators. These operators have correlation length, which is of the length of the lattice spacing, not of the length of the continuum limit. As a consequence of that, the low energy theory is robust against symmetry violating deformations. We can turn on e to the I phi in the continuum limit, and the low energy theory doesn't change. As a result of that, there's also no BKT transition. Let me give another manifestation of this result. We discussed the plane waves and the charged states. The plane waves have energy of order 1 over L squared. This is finite in the continuum limit, and we can write it in terms of the lattice parameters, the number of sites square times the lattice spacing square. And the charged states have 1 over LA. So this is infinite in the continuum limit. And in terms of the lattice parameters, it also has the 1 over A squared, the same A squared as in the plane waves, but only one factor of L in the denominator. We are interested in the limit L going to infinity, namely the number of sites in the lattice goes to infinity. And we can take this limit 2 different ways. Option 1, we take what we've described, the continuum limit. We take the lattice spacing going to 0 with fixed size of the box. So we put the system in a box, and we take the limit such that the lattice becomes finer and finer. There are more and more points in the lattice, holding the size of the box fixed, so that we should get some field theory, or whatever we get, in finite volume. This limit kept the plane waves and pushed all the charged states to infinity. After we have done that, we can also take the size of the box to infinity. We can also take the limit in the opposite order, which we can call the thermodynamic limit. We take still a number of sites to infinity, holding the lattice spacing fixed. But if we do that, if the lattice spacing is fixed, then the size of the box goes to infinity. So what we do is not make the lattice finer and finer, but instead we make the lattice bigger and bigger. As we take this limit, all these states come crashing down to low energy. And later, if we want, we can take A to 0. So the spectrum in these 2 ways of taking the limits, first A to 0, or first little L to infinity, the spectrum is not the same. So taking the continuum limit and taking the thermodynamic limit, these two limits do not commute. This is clearly a UVIR mixing, and I'll say more about that later. The main point here is that the way we take so everything on the lattice makes sense. We have a finite lattice spacing. Everything is nice and finite. And now we start taking limits. And normally in field theory, the continuum limit and the thermodynamic limit commute. In fact, the preferred way for a field theorist is to say, first we take the lattice spacing to 0, holding the size of the box fixed. And then we take the size of the box to infinity. And it doesn't matter in which order we do that. Here, there's actually a difference, and this is the hallmark of the UVIR mixing. And this is really the source of the problem in formulating a quantum field theory for these exotic lattice systems. We can get the same insight and understand it even better if we study correlation functions. So this is, again, a very meaningful thing to do. We can do it on the lattice, or we can do it in the continuum. And we can do it on the lattice, get final answers, and then start taking limits and see what we find. So we have studied many correlation functions. For example, we can study the 2-point function of derivative of phi with respect to tau. or 2-point functions of exponentials. We also studied various 4-point functions. And once we have a correlation function on the lattice, we formulate it such that the whole thing is solvable already on the lattice. It's not the version that I presented, but there's another version of the system where everything is solvable on the lattice. So we take these closed form expressions, they're closed form but complicated, and then we take two different limits. The number of sites going to infinity, and we can do that together with the lattice spacing going to 0 with fixed volume, or in terms of positions of operators, these x and y, we hold them fixed in space. So for example, if we look at this correlation function, or at this one, we hold the number of sites in tau keeps growing such that the total time length remains fixed. Or here we separate in x and y, with x and y are not positions on the lattice, but they're positions in space. This is the distance between the points, and we make the lattice finer and finer in between. And then we can take the infinite volume. Alternatively, we can hold the lattice spacing fixed, take the number of sites to infinity, and then the operators are at fixed positions on the lattice. And then later, if we want to do that, we can take the lattice spacing to 0, which means that the operators are separated more and more in terms of lattice spacing. And to give you a spoiler, again, these two limits will not commute. This correlation function, in taking the two different limits, do not commute, again, signaling the UVIR mixing. Let me give you a demonstration of that in this 2-point function. If we take the continuum limit and infinite volume of this 2-point function, we do it on the lattice, we take the limit, and we get a closed form expression which simplifies in various limits. Tau much less than x times y, we get some power behavior. So that's not very shocking. That's what we would expect in any field theory. If we set tau is very small compared to the distance, we can set it here to 0. And as the two operators separate from each other, the correlation function decays like a power. A more interesting limit is tau much bigger than x times y. So we get a prefactor, which is a power. That again follows from general scaling. But there is an interesting factor here of the log of tau over xy. Now, for generic x and y, this is the answer. It's finite. We can take the limit in any way we want. Everything is fine. But the singularity here is xy equals 0. See, here I cannot discuss the singularity as x times y equals 0 because I assume the tau is much less than x times y. But here tau is much bigger than x times y. So I can ask what happens at xy equals 0. This is very surprising because what we see here is two operators at different Euclidean times. So they are not at the same point in space-time. I can even keep their x different, but they have the same y. So I have two operators at different times, at different x, but they happen to be at the same y. And the correlation function diverges. So the correlation function diverges at the place where there's nothing there. So I just looking at the 2-point function and I move 1 point relative to the other, and all of a sudden it diverges. Is this a UV divergence or is it an IR divergence? That's very confusing. And the way to answer that is that we go back to the lattice and we take the limit more carefully. So if we look at the lattice, the divergence is absent. And the divergence appears either as so if we send A to 0, we keep the finite size of the box fixed, the divergence is absent. Or the other way around, we send A to 0, but we work in finite volume, again, the divergence is absent. So this divergence here arises either from the UV or from the IR. And there's no way to tell whether it comes from the IR or the UV. Again, we interpret it as a UV-IR mixing. And that can be understood in a lot of detail, and I don't have time to do that here. So we see that from the correlation function, this correlation function, we also see this UV-IR mixing. The more interesting correlation function is a 2-point function of the exponential. Recall that, so let's go back. The analogous calculation in the 1+1 dimensional compact boson, this is the propagator. This is d by dz phi with d by dz phi, which is 1 over z squared. So that's kind of similar to this power behavior here. the log is peculiar to this system, which makes this system more interesting. This is the analog of the two-point function of e to the I5 with e to the minus I5. Because of the subsystem symmetry, the two operators have to be at the same position. Otherwise, this correlation function violates the subsystem symmetry. But we can have them at separate times. So this calculation can be done, and it decays exponentially with tau over the length of the systems times little a. So if I take the continuum limit, it goes to 0. Or if you wish, the correlation length or the correlation length between these two operators is of the order of 1 over the lattice space. That is of the order of the lattice spacing. So in the continuum limit, these two operators vanish. They are redundant operator. And this is consistent with what I said earlier, because I said that the states that come between them are these charged states, and they have energy which diverge in the continuum limit. We can also see it from here, because the exponential suppression is the time difference between the two operators times the energy of the lowest lying state, and the lowest lying state has energy 1 over LA, which diverges in the continuum limit. We can also study the same correlation function in the other limit. L goes to infinity with finite A. In fact, this was computed already in the paper of Paramakanti, Balance, and Fisher, except that we did it using a different formalism. And we reproduced their answer. So this is the two-point function in the other limit. And it's again very strange. In the compact boson case, we have a power of tau here, and the power of tau appears e to the minus a log. Here instead, we have e to the minus log square. This means that this two-point function decays faster than any power of tau, again signaling that these operators are very strange. Another peculiarity here is that the A dependence in the correlation function cannot be absorbed in wave function renormalization of phi. Normally, such A dependence on the cutoff is absorbed in redefining the operator such that the correlation function becomes finite in the limit. Here, we cannot do that. So all these facts mean that as we try to define the continuum limit or the thermodynamics limit or whatever this operator vanishes in the low energy theory. It is a redundant operator. I'm approaching the end of my time, so let me summarize what we have seen. I started the talk by summarizing the lore. That the low energy of any lattice system with local interactions is expected to be captured by a continuum quantum field theory. And this lore has been dominating condensed matter physics and was very influential also in the context of high energy physics for decades. But various exotic lattice models challenge this expectation. And these models have several characteristics. Most of them I did not discuss, but fortunately, we just heard a beautiful talk discussing these elements. And the elements are subsystem global symmetry. I did discuss that, but it also appeared in the previous talk. As a result of that, we have some discontinuities and even singular observables in the continuum limit. I did not have time to discuss it here. There's large ground state degeneracy. This was mentioned in the previous talk. And defect with restricted mobility. This was also mentioned in the previous talk. And if you go deeply into the various models, you can see how all these facts are intimately related to each other. They're not kind of logically, they're not independent of each other. In the example I discussed here in detail, we don't have many of these features, but we do have the subsystem global symmetry. And the existence of the subsystem global symmetry led eventually to all these subtleties of states with the infinite energy that contribute, and UVIR mixing and so forth. So this brings me to this UVIR mixing, which my understanding is that this is the most peculiar thing about all these exotic models. That the long distance physics is very sensitive to phenomena at very short distances. Most of the information in the short distance theory is washed out by the time we take normally is washed out by the time we take the continuum limit, but this is not the case here. And the long distance behavior is very sensitive to some short distance details. And this is a bit reminiscent of UVIR mixing which is common in various string constructions. And in this audience, I think people will be easier for the audience to relate to these. The little string theory exhibits one kind of UVIR mixing because it has T-duality, the local operators do not exist, and so forth. And also, ordinary field theory on the non-commutative space also exhibits UVIR mixing, where there are infrared singularities, which started their lives as ultraviolet singularities. So the ultraviolet behavior of the model translates into infrared singularities. And the physics of these UVIR mixing in non-commutative spaces is actually not unlike the kind of singularities, the kind of UVIR mixing that we see here. The origin of the UVIR mixing in theories of non-commutative space is that these theories, although it's not obvious from the original formulation, are described dipoles. As we make the dipole more and more energetic, it actually grows in space. And since if it has more momentum in the x direction, it becomes bigger in the y direction. And therefore, the UV singularity in the x direction translates into an IR singularity in the y direction, which is a bit similar to what we saw in this talk. Also, it's similar to what we have here because of the appearance of dipoles. So these are all these exotic models. And there are various peculiar quantum field theories that capture these facts. I discussed one of them in this talk, but during the last 2 years, we wrote many papers, the same group of authors with Pranay, Hota, Shuhen, and Shuhen. And they involve very peculiar field theories, which we analyze in detail. And the peculiarity of them is that they involve discontinuous fields. But perhaps the most exciting thing about that is that there are many, many interesting puzzles that I don't know the answer to. And that's why this field is exciting. Thank you.
Thank you, Professor Seiberg, for a very nice talk. So now I invite people for a question. I see Sunil has a question. Please go ahead.
Yeah, that was a beautiful talk.
Yeah, Sunil.
Thank you very much.
Thank you, Sunil, and it's good to see you, and I'm looking forward to seeing you again soon.
Yeah, me too. So I had a naive question. You know, you had some parameters in your original Lagrangian, some mu and mu naught, and you said there's some exchange duality. But then somehow this, in the 1+1 compact boson, there's actually a duality which has a fixed point where we get an enhanced symmetry. So is there any special point in the parameter space of these models where anything new happens?
I doubt it, because these two models, you see, in the 1+1 dimensional boson, the parameter, say the radius, is a dimensionless parameter, and it's an exactly marginal deformation. And the spectrum of the theory depends on the value of this dimensionless parameter.
So here it doesn't.
Mu and mu0 are dimension full.
Mm-hmm.
And in fact, there's a scaling symmetry that allows me to set them both to be 1 GeV or 1 kilogram.
Okay.
So there's no spectral point. And indeed, if you compare with the compact boson, the plane waves don't do anything exciting. All the excitement there comes from the charged states. Right? The charged states have energy R and 1 over R. The plane waves have energy of 4 over 1.
Mm-hmm.
Now, the analog of that here is that the plane waves are the plane waves here with their peculiarities, and all the charged states are gone. All the momentum states and the winding states are not present in the continuum theory. They exist on the lattice, but not in the continuum theory.
I see.
Just to kind of to show you the interest, to show you it's more interesting, in some other versions of this model, the charged states are present. And there your question is meaningful, and then the situation is subtle for other reasons.
I see. Thank you.
Shiraj has a question. So please go ahead, Shiraj.
I know you. I know you.
Thanks for the spectacular talk. It's a very vague question, but in the non-commutative theories, you could. There was this interesting star product whose structure exhibited this UVIR kind of mixing. I was wondering whether there's any sense in which there is an interesting product in some of these theories, perhaps through some operator algebra or something like that. Sorry for the
it's a fantastic question. I do not know a satisfactory answer, and that's the quick answer. The quick answer is that I do not know the satisfactory answer. But there's a deeper answer that I would like to give, and that is that these theories have this subsystem symmetry. Some versions of it do not have the full subsystem symmetry, but have only a dipole symmetry. These are the kind of symmetries that figured in the previous talk. So that I can easily write a Lagrangian for them. Here I have dx dy phi 180 square. There I have di dj phi 180 square. So I have both the x square and the y square and the x dy. So I have more terms in the Lagrangian. And since I have more terms, I have less symmetry. But still there's an enhanced symmetry compared with the regular one. This enhanced symmetry is what's special. In the case of the non-commutative geometry with the star product, there is no special global symmetry associated with it. So my view on this subject is that, again, it's because of my upbringing and my background in field theory, is that I always go after the symmetry. Once confused, this is one of my mottos, once confused, you go after the symmetry. And these systems have indeed very peculiar symmetry. That's not the case in the non-commutative geometry case. So this is not a satisfactory answer, but I doubt there is an interesting star product here. Another way of saying it is that you can analyze higher dimension operators. You ask, what else can we add to this system? Can it change the story here? And in the case of non-commutative geometry, it's very important that you have the whole power of higher derivatives in order to have the star product. That's not the case here. Here we just keep the lowest order terms and the higher order terms are irrelevant. So this story is also, so recall in your paper on non-commutative geometry, the higher derivative terms, kind of terms with four derivatives, you expanded in derivatives, all of them are crucial in order to tame the UV divergences. The UV divergences are tamed by an exponential of a derivative, not by having just a finite number of derivatives. Here, the whole structure comes from just finite number of derivatives. But I gave a long answer because I don't know the answer. Usually, if I know the answer, it's short.
Thanks a lot.
Vijay has a question. Please go ahead.
Thank you, Professor Seiberg, for a very nice talk. I had a question regarding the RG of your theory. So if I just do a simple, probably naive RG, I will get a second derivative term at the first one loop, right? I mean, because I have this dx dy phi, dx dy phi, dx dy phi. So I can actually have two higher momenta ones which will give me a first derivative. Is it possible?
No.
That is, I'll get.
No, you don't get, if you start computing, so first of all, this theory as it stands is free. So the renormalization group is trivial. The theory is actually scale invariant.
Yeah.
So this continuum theory is scale invariant and is not changed under renormalization group. So I could rephrase your question about doing it on the lattice. Imagine
yes, with the cosine, yes.
Okay, if you do it with the cosine, you could ask, then it's different. So I can give you several different answers. First, if you go all the way to the infrared and you found the continuum theory I described here, and you fine-tune whatever you need to fine-tune, then you could ask, how do we check whether it's robust or not? We try to deform the low energy theory. So whatever deformation we have at short distances translates to something at long distances. So we should check what are the different operators in the long distance theory. This will check the neighborhood. I don't know how to do it in general, but we can do it when the deformation is infinitesimal. And under infinitesimal deformations, these operators that you mentioned are not generated. In fact, these operators that you mentioned violate the symmetry of the model. So if we formulate this model while preserving the subsystem symmetry, the operators you mentioned violate the subsystem symmetry, so they're not going to be generated.
Yeah.
I'm making a stronger claim here that even if you violate the subsystem symmetry, all the operators that violate it are irrelevant at long distances. In fact, they are infinitely irrelevant. That's why there is no BKT transition in this model. They exist in the cosine model, but not in the continuum model. So I don't even need to impose the subsystem symmetry. I can just go to I impose whatever I need to impose, find this infrared behavior, and then I explore its vicinity. And the vicinity is clearly unchanged by operators, as you mentioned, because these operators violate the symmetry. And I make seconds more than that, even if you violate the symmetry, it's still stable. Perhaps by a small amount. I'm not guaranteeing the size of the stability region, but they are robust in that region.
Yeah. Thanks so much.
Thank you also for your talk.
Thank you so much. Yeah.
Quite beautiful.
Okay, one last question by TIFR.
Hello, Nati. Thanks for a fantastic
talk. Hi, thank you.
So
I don't see you.
Oh, I don't know. The camera should be on. I don't know why.
Oh, now I see you. You're far from the camera. You're outside the frame. Yeah.
Oh, okay.
Good to see you.
Yeah, so it's a two-part question. You wrote down this continuum description for a particular way of taking the continuum limit, where you take the small L fixed and then take the lattice spacing to be small, making it finer and finer. And also there was, I mean, one could do it another way where one would take thermodynamic limit. So would there be a separate kind of a continuum description for that limit? And I guess the second part is that, you know, this UVIR mixing, which one could see from the non-commutativity of these two limits, whether that can be diagnosed purely from the continuum point of view.
Yes. So the answer to, well, let me answer both questions. Question number one was, the field theory that I described fits nicely with what I call the continuum limit. Namely, the lattice, this volume of space is fixed, size of space is fixed, and we make the lattice finer and finer. That's usually what high energy physicists call the continuum limit. When people do, say, simulations of QCD, that's what they do. They define QCD in finite volume by making the lattice spacing finer and finer, because there's a continuum field theory in finite volume. This is the Lagrangian that I described. You could ask, what about the other limit? So first of all, you can take whatever limit you want. There's a lattice model, you can take whatever limit you want. You either get something interesting or not. Usually when you take continuum limit, you take whatever you do with the lattice spacing, and then you perhaps tune some coupling constant to a critical point, and you have to do it at a particular rate such that you get something interesting. What happens in this case is that if you try to take the other limit and you try to see what you find, and try to find some effective description of the low-lying modes, it is very singular. So in the other limit, the spectrum, for instance, there's a lot more states at low energy, because all the charge states also come crashing down. The theory that I presented here is scale invariant. In the other limit, even the results are not scale invariant. So the other limit is a very singular limit. And the literature is full of people who analyze the other limits, and they didn't know that there are these two different limits. But what they did was effectively to study the other limit, and it was very, very confusing. So my take on that is that there is a limit that gives you a continuum field theory in finite volume, and that's what we should be studying. There are various other limits which are more singular, and if you want, you can study them. Then you had another question which was also interesting. Can you remind me what it was?
Yeah, is there a way to diagnose UVIR mixing directly from the continuum point of view?
Yeah, so it actually, everything comes just from the continuum point of view. Where can I go back? Okay. So here is, for example, so this is a continuum computation. You look at this Lagrangian, there's a Green's function. You can compute this two-point function using the Green's function. That's what you find. Everything is nice and finite. And then you ask yourself, what is the meaning of the singularity here? Why is there a singularity when two operators are not at the same time and not at the same y, but they're simply at the same x? Yet the two-point function diverges. And you can see that you regularize it, and actually it doesn't matter how you regularize. You can think of it either as a UV mixing or as an IR mixing. So you can ask yourself, where did this come from? And it came from the fact that the energy of the plane wave is P of x times P of y. So you can have states with very low energy with arbitrarily large px, provided py is sufficiently small. And you can have states with low energies with arbitrarily large py, provided px is small. And you can cut off this divergence either by making px not grow too much, or making px not go too small. So you can regularize, it's either in the UV or in the IR, still keeping the energy finite. So what does this thing mean? Finite tau probes finite energy. You see that if I hold y fixed and send x to 0, it probes large px. And the theory has low energy states with finite py, with arbitrarily large px, provided py is small. And that's what gives this divergence here. That kinematics is a bit similar to the kinematics in the non-commutative space. With the x and y kind of act in opposite ways.
Yes, thank you.
Somdatta has a question, so that will be the last question. Somdatta, please.
I was just wondering whether you can couple the scalars to gauge fields, and you can have a theory of scalars and gauge fields where you can have higher dimensional operators with phi sandwiching, with 2 phi sandwiching 4 Ds, and make it a gauge invariant operator, such that when you analyze the theory, you have a similar theory to what you had with the kinetic term, the usual f mu nu, and the higher order term supplying that sort of terms that you were considering. And I was just wondering whether these sorts of theories can be analyzed in order to get the sort of fracton behavior that the previous talk was considering. Yes. And kind of get the sort of behavior of having a single charge not separating from the body and 2 charges separating from the body in order to give something like confinement.
Okay, so let's first get confinement out of the way. There was a question about that. The phenomenon of fractons has nothing to do with confinement, just as the previous speaker mentioned. Another way of saying it is if we put probe particles in a confining theory, the energy of the state grows linearly in the distance between the 2 probe particles. Where in the case of fractons, the energy is independent of the separation between the particles. So first of all, we get confinement out of the story. I presented now to your other question. I presented here one model which has only a free scalar field, no interactions, no gauge field, is the baby version of everything. This is kind of the starting point. It's like when you start learning quantum field theory, you start from a free scalar field. This is the first example you study. Now you can couple this system to gauge fields, where the subsystem symmetry becomes the gauge symmetry. Or you can study the gauge fields on their own, the gauge fields without the matter theory. Most of the condensed matter literature, and also in the previous talk, you saw some discussion of this classical theory, where the speaker wrote the analog of Maxwell's equations for such a scalar field coupled to the gauge fields. Much more interesting is to study the quantum theory. And in the case of the pure gauge theory, we have done it in a lot of detail in our papers. You can also Higgs these U1 gauge symmetries and have Zn versions of them. And I did it here in 2+1 dimensions. You can do it in 3+1 dimensions. So we have analyzed of the order of, depending on how you count, of the order of 40 different models, with kind of doing all sorts of things like that. Not all of them at the same level of detail. And for the purpose of half an hour talk, which is now almost 50 minutes, I picked to discuss only one particular example, the simplest of them. But there are many other knobs you can turn.
Okay, thanks.
Okay, so thank you, Professor Seiberg, for a very beautiful talk and the subsequent discussions. Thank you very much.
Thank you.
Alok has suggested that we will